Okay, so rational functions, but this time special features of rational functions. So thus far we saw that. That sounds kind of awkward, whatever. Rational functions can have vertical asymptotes and horizontal asymptotes, but do they always have them? So based on what we know, state the equations of the horizontal and vertical asymptotes of the following functions without using technology, and then we'll just graph them using decimals. Right now, obviously, you'd be expected to graph using your graphing calculator. So what's the horizontal asymptote here? 5/3, right? So it's horizontal, so it's going to be y is equal to 5/3. And what's the vertical asymptote? X equals -4/3. Okay, so let's check that out. It's not quite. Divided by, what is it, 3x plus 4? Okay, so we've got horizontal asymptote, which is running somewhere around here. Vertical asymptote, sorry, horizontal asymptote running somewhere around here. What did we say it was? 5/3? So maybe just change the scale a bit. Let's do this. No, that's the wrong way. Okay, so horizontal seems to be around here, and this is 1, 2, 3, 4, 5, so it's tending out. Looks like it could be 5/3. And then we said -4/3, so 1 1/3. That seems reasonable. Let's do this one. Y equals 3x over x squared plus 4. So what's the horizontal asymptote? So we'll be looking at kind of 3 over x. What happens when you divide 3 by x? 0, right? Because the x is going to get larger, right? So when we're looking at horizontal asymptote, we're looking for large values of x. This is going to end up being essentially 3 over x. So y is equal to 0. And what's the vertical asymptote? Well, it should be the root of -4, but it really wouldn't matter because it's there is none. None. Since we cannot set this to 0, right? We can't make x squared plus 4 0. All right, so what was that? 3x over x squared plus 4? So this is x squared plus 4. And the top is just 3x. Okay. So we got some little jumping around going on here. We can see the horizontal asymptote is tending to 0. And we don't see any vertical asymptote. 8x cubed plus 5 over 2x cubed plus etc. So what's the horizontal asymptote? 8/2. We can rename that 4. So y equals 4. And what's the vertical asymptote? Okay, so this might take a little bit of work, right? We're gonna have to we got to set 2x cubed plus 4x squared minus 16x equal to 0. So we could factor out. We could actually factor out a 2x, right? X squared plus 2x minus 8.
Oh, right.
So we got 2x. We got x what? Plus 4 and x minus 2. All right, so looks like we could have a few vertical asymptotes, right? When x is 0, when x is -4, and when x is 2. All right, let's take a look to see if that's actually true. So what's our equation? Y equals 8x cubed. You could have said, you know, nothing's happening. Y equals 8x cubed. Was it plus 5? Plus 5 divided by, okay, what do we got? 2x cubed minus 4x squared minus 16x. Okay, so where do we say we had asymptotes? So 0, yeah, looks like one there. Where else? Negative 4. 2, 3, 4. Seeing something closer to here. So did I get the signs wrong on this? Did I get the signs wrong on this? Okay, factor out of 2x. Did I get the signs wrong typing it in? Yes, I did. So, should that be? No, I didn't.
Yeah, it should be 2x cubed plus 4.
Oh, plus 4x squared. All right. My photocopy didn't look so hot. Okay, now we got there, minus 4. And if we zoom out more, okay, then we can see a little better. So minus 4, 0, and 2. Okay. Good. Zoom in a little. So far, so good. For the rational function, y equals x squared minus 5x plus 6, where is the vertical asymptote going to be? Well, don't say 3. Say x equals 3. Use the GDC to, okay, so we'll graph x squared minus 5x plus 6. Okay, we got y equals x squared minus 5x plus 6. So you can follow along on your own calculators. Where's the asymptote? Where's the asymptote supposed to be? At 3. All right, so let's see what's going on here. Fine. So I could trace along and see there's the point 0, negative 2. There's the point 2, 0. Oh, what's it say? 3 and undefined. So what we have here, the function is not defined at 3, right? Now, that makes sense to us. We know, but we were expecting an asymptote. So what's going on? Right? That's the question. Why is this not an asymptote? Okay, so we sketch. What do we get? The sketch looks like this. Was the graph you expected? Or did we get what we expected? No. Expect to see an asymptote. Use your rational expression skills to simplify this. Okay, so we got a factor. So how will the top factor? X minus 3, x minus 2, right? Do quick FOIL to check it. Okay, x squared minus 2 minus 3 is minus 5x plus 6. Okay, well, what do we do with the x minus 3's then? We cancel them out, right? Now, before we do that, we should state that x cannot equal negative or 3, right? X can't be 3. And then we cancel it out. So we can say that the graph that we expect to see the graph of y equals x minus 2, which is actually the graph we saw, right? It was a straight line. But it's undefined when x is equal to 3, right? We're not allowed to have x be 3. So these guys will cancel out, but you still, it's there in the thing. So when you put a 3 in, you get undefined. The simplified form fit with the graph. Yep, that's what we saw. When we traced along the graph, we saw at 3 it was undefined. You might think the graph of y equals x squared minus 5x plus 6 or x minus 3 is identical to y equals x minus 2, but it isn't. You could do this fancy graphing window on yours, but basically we've gone through, we've traced it out, and we see that what happens is there's a hole in the graph. Okay? We call it a hole in the graph. It's undefined, but only at that one point. The hole in the graph. At the point, and it's at the point, what, 3? Well, what would it be? So we're looking, here we go, 1, 2, 3, 1. It's at the point 3, 1. Okay? Because there is no point 3, 1 on this graph, actually. So at the point 3, 1. the graph is not continuous at the point 3,1. So if you're going to draw the graph, you can draw it, but then you have to lift your pencil and put it back down. So we mean by not continuous. And we say it has a point of discontinuity. The word for the day is discontinuity at 3,1. Adjust your graph in question 2a to include the point. So what we should do is indicate that at the point 3,1, we have a hole. So we're going to show it as a point discontinuity. Just put an open circle there. Now, it's really a point. A point is dimensionless, right? It doesn't have any size. So, but for us to indicate it, to show everybody, say, hey, look, it's not defined here at that point 3,1. The x-coordinate of the point of discontinuity is the, so what value from here? It's the non-permissible value, right? Non-permissible. Because it's when x equals 3. So remember, non-permissible is equal, a restriction is not equal. It's a non-permissible value of the original. Substitute this x-coordinate into your answer in question 2D. Okay, what's 2D? So in 2D, y equals 3 minus 2, you get y equals 1. So in the simplified equation, it is defined, right? And we say it's the point 3,1. But in the original equation, and that's what we're always basing on, in the original equation, it is not defined. Right, that is a restriction, it's a non-permissible value, so we can't use the number 3. Yeah, question? Nope. Okay. Substitute this coordinate in, do you get the corresponding y-coordinate of the point of discontinuity? Yes, we do, right? So when you go into the simplified equation, you're going to find out where the hole in the graph is, or where the point discontinuity is. Use a GDC to complete the following table. Graph, look for any points of discontinuity. Okay, do you want to do another calculator or just do it in decimals? Calculator? Okay, get your calculator out and do it. I'll do it up here in decimals. So remember, if you're doing it at home, or if you're doing this on a quiz, you have to use your calculator. If you're going to go for point discontinuities, set your window to the values that are given. All right, I'll get the calculator up too, because it's what we have to use. Anybody have like a TI-83? Okay. If you got a plain old 83, it's not going to look pretty. Okay, you grab, because the TI-83 isn't smart enough to know how to handle these things. Okay, anyway, just see what you see. X squared minus x minus 2 divided by, and we got x squared minus 4. Go. And the window I want was negative 4.7. Not 47, 4 point. It's negative 4.7. So reset your window. And negative 5 to 5. And graph. I messed up now. That's totally good.
Scale 5 to 10.
Yeah, okay, I put the scale as negative 5, that's a 1. And then negative 5, 5. If you mess up and your graph's doing weird stuff, and it's not stopping, just hit the on key. It's like a brake button. And it'll stop it'll stop it from graphing, because otherwise it's going to want to keep going. Okay, so there's our graph. Look closely for any points of, I don't know, do you see anything on yours? Yeah, I don't know what you're going to see. I mean, I could trace over, let's see, tracing. Yeah, I don't know. If I go into the table, we are going to see that at 2 it says error. Okay, so I don't know, man. The calculator with the fancy tech, whatever. If we graph the graph, draw the graph though. Go back to the graph. So we're looking here at -2. We've got something going on. Okay, so this is x equals -2. Where's our horizontal asymptote? Where is it? Y equals
0.
1. Okay, so we got something going on here, like this, and then we've got something going on here. If I make y, well, let's just, okay, it looks like it's going through 1 here. So what's it doing? Going like this, and this. Okay, but we saw, wait, there's something happening at 2. There's a hole, a really big hole. Okay. All right, so that's what we're looking at. The equation of the vertical asymptote, there is only one. We just see it as x equals -2. Equation of the function in factored form. So to really drill down to what's going on here, we're going to factor this thing. So we've got y equals, okay, so I've got x minus 2, x plus 1, and I got x plus 2, x minus 2. So from the factored form, I always look at the, when you're working with rationals, you look at the factored form of the denominator, and that's what you use to state your restriction. Okay? Remember, we're always working from the original equation. Yes, this simplifies, right? And it becomes y is equal to x plus 1 over x plus 2. So the graph, excuse me, the graph that we're going to get is the same as the graph. So if we graph x squared minus x minus 2 over x squared minus 4, we get the same graph as if we graphed x plus 1 over x plus 2. Right? It has the asymptote at -2, right? There'd be an asymptote because this will be 0. We'll end up with something over 0. That's the asymptote. But there's also, in the original, something going on at +2. Okay, what's going on at +2 in this case? So when these guys cancel, when these factors cancel, this is where the point of discontinuity is. Okay, if this factor doesn't cancel, it's still down here, then there's an asymptote. So in this case, we have asymptote. These guys would cancel. That's the point of discontinuity. Okay, so we could say, we've already done the asymptote here, so we say we have a point of discontinuity, or a pod, at x is equal to +2. If we want to say, where is that point, then we just plug it into here and work it out. Okay, so what's the y coordinate? Because here it exists. +2 is perfectly fine to put into here, right? So we're saying, hey, this graph is the exact same as this graph, except when x is equal to +2, where on this graph it exists and it's 3/4, and on this graph it does not exist. It is a point of discontinuity. So where is the point? It's at 2, 3/4. Okay, so then y is equal to 2 plus 1 over 2 plus 2 is equal to 3/4, and the point of 3/4. 3/4, and so the point of discontinuity is 2, 3/4. Okay, so if we were to trace along the calculator as we get close to 2, it's going to be getting close to 3/4, right? So that's 0.758, 0.75, right? So we can see we're getting close to 3/4 there. Okay, now calculator is unreliable then, right? It's not showing us. There's no little hole in the graph, no little blank spot or anything like that. Even on Desmos, there's no hole, right? It draws, because it's really, it's a point and it's dimensionless, right? It's just at that one tiny place. But if you do trace along in Desmos, then it'll say, oh, undefined, right? How do we know where? We look here, okay? We look at the factored form. We look at the factored simplified form. This is the asymptote. This is where the discontinuity will be. Okay, so let's try that on this guy. X squared minus 5x minus 6. Maybe we should predict this ahead of time. So what would we do? We'd factor it, right? So what is that? X minus 6. So x squared plus 1x minus 5x minus 6, and x plus 2. Okay, wait. So what's happening at plus 2 and minus 2? There's asymptotes, right? Nothing canceled out. This didn't simplify down to something else. So it tells us that at positive 2 and negative 2, so x equals negative 2, and x equals positive 2, that we have asymptote. Okay, so we can go graph this then. Let's go graph this. Y equals, so x squared minus, I'm just going to insert a 5, minus 5x minus 6, and it's divided by x squared minus 4. Okay, graph. Okay, so there's one at 2, negative 2. And here's one at positive 2. Okay, and where's the horizontal asymptote? X squared over x squared? 1. Okay, so there's going to be a horizontal asymptote here at y equals 1. What did this guy ask for? The equation of the asymptote. So x equals 2, x equals negative 2. List them separately. Don't write x equals plus or minus 2 there.
How did you insert the 5 without it deleting?
So what I do, you go second function ins. There's a key that says insert, it's like delete. It's on the delete key, but it says insert. So if you type that, then you can start inserting stuff. Okay, and then when you arrow over, then it just goes back to non-insertion mode. It's just easier, right? Or you retype it.
Why is it right? X plus minus 2. Well, x is plus minus 2.
Why wouldn't you write that? We're writing equations of asymptotes, so there should be 2 separate equations. Here, when you're writing, if you're writing the non-permissible values, you would say x equals plus or minus 2. But restrictions, x equals plus or minus 2. But if it's asymptotes, list them separately, right? So there's 2 of these guys. Okay, then what did our graph look like? We had this going on. And in here, we had something like this. And over here, we had something like this.
If you graph like y, it still gets to the point of intersection.
Sorry? What was that?
So like for the graph, you can also graph y equals 1, so like where the horizontal asymptote is, it still gives you a point of intersection.
Here? Yeah. Okay, so the observation was, if I graph y equals 1, then the graph is intersecting the horizontal asymptote. And the answer is, it's okay. So horizontal asymptotes are defined when x goes to infinity or negative infinity. So we're interested in what's going on out there, not what's happening in here. So you can cross an asymptote. You could get curves that'll do this and then come down to it. Okay? So you can have all kinds of behavior in here. That's fine. When we talk asymptote, we're talking about as x goes to infinity. So I'd be better off, doing like a standard window here or something. We just would see more of it. But it's really, what's the behavior of the graph as x gets really large at a positive or negative value? Okay. See, and there's your now you can see it's really getting close too. And there's getting close. So asymptotic behavior for a horizontal asymptote, it's not what's in close, it's what's out far. Although both of the functions have the same 2 non-permissible values, the second function has 2 vertical asymptotes, and the other function has 1 and a point of discontinuity. Use the factor form of the equations to explain how to determine whether there will be an asymptote or point of discontinuity. So we've talked about it, let's just formalize it. So if a non-permissible value, also makes the numerator 0, so we'll just scroll up and take a look at that. Numerator 0. So here, the non-permissible value of positive 2 makes the numerator 0 as well. Okay, so in effect, what happens? Well, these guys cancel out, but there's still that point of discontinuity, right? Where it is, that function is the same as this function, except at these 2 points. So if you also, excuse me, if you also get a numerator of 0, or if you have a common factor top and bottom, that's really the same way of saying that, there will be a point of discontinuity. So if you have a common factor top and bottom, that will be a point of discontinuity. Otherwise, it'll be a vertical asymptote. So if it's only the denominator, which evaluates to 0, then there's a vertical asymptote. So otherwise, there will be a vertical asymptote. A vertical. So very important when you're working with rationals to be able to factor them, to state the restrictions from a factored form, and then to look a little deeper into it, right? Oh, these guys are the same. Oh, there's going to be a point discontinuity here. Or point of discontinuity. Okay, for this, the non-permissible value is... So remember, non-permissible value is stated as a positive. X equals. What does X equal? -1. What's the answer to be? Well, the only way we can find out is to do what? Factor the numerator. So I'm going to assume there's a point of discontinuity by just trying x plus 1, and then this will be 2x plus 5, and then I'm going to check it. And it is. Okay, so I went with the assumed factor. Hey, let's say there is a factor of x plus 1. I'll do it. Okay, then we know now there is a point discontinuity. So point of discontinuity. So I'm going to call POD, or it's going to run into my graph. What's the simplified form of the equation? Y equals 2x plus 5. What are the coordinates for the point of discontinuity? So what do? We plug -1 in for x, right? Because that works here. This is just straight line. That's continuous, right? So we go y is equal to 2 times the non-permissible value, -1. So y is equal to 3. And the coordinates of the point then are -1, 3. Okay. And the x-intercept. Well, let's do the y-intercept first. What's the y-intercept? 5. What's the x-intercept? -5/2, right? I'm going to set y to 0, subtract 5 from both sides, etc. Sketch the graph, labeling the intercepts and the point of discontinuity. Okay, so if I'm going to sketch this, if we give you this, we'll give you a nice grid. So on the nice grid, you'll be able to find the point. So here I'm just going to put in a scale. -1, -2, -3, -4, 1, 1. Okay, 2x plus 5. 1, 2, 3, 4, 5. Go down 2 over 1. Oh wait, but that's -1, 3. That's really actually where the hole is, right? That's where it's a hole in the graph. It's a point discontinuity. Go down 2 and over 1. There's another point. So I'm going to draw this like this. And then go 2x, 1, 2. And so on. Okay, so this is -5/2. This is 5. Okay, so we've got our, what did it say, label the intercepts and the point of discontinuity. So if we want to label that, we can throw the coordinates on there. It's the point, negative 1, 3, or is the lack of point there? Sketch rational, maybe the intercepts point of discontinuity. Okay. So there's a whole analysis of a rational function, right? So here's a rational function. What is, okay, we know something's going on at negative 1, and now we know there's either an asymptote or a point of discontinuity. How do we figure out which? So we go to the factored form. Then we say, since the numerator would also evaluate to 0 at negative 1, it's a point of discontinuity. Okay, and then we carry through. So this graph here is the same as the graph of 2x plus 5, right? If I just gave you the graph on paper, it would be indistinguishable if I don't show you this. If I show you this, then you start to say, hey, I know then on the bottom there's a factor of x plus 1, right? Because that gives me a discontinuity at that point. Which is, I think, where the next thing leads. Oh, not quite the next. A rational function is given by, what's the equation of the horizontal asymptote?
Y equals 1.
Y equals 1. So just cover up anything that's it doesn't matter, right? Like when it's a trillion that's being squared, subtracting 2 trillion is going to make a heck of a difference. Okay, because that's like somewhere 100 decimal places that way. Express the equation in factored form. Now you can see how it is important to factor, right? Because everything will be wrong in this question if you have the factored form wrong, right? Everything from that point on. You'll have the wrong asymptote. You'll have the wrong point of discontinuity if there is one. Or you'll have things where there shouldn't be things, okay? And you'll turn a question which could nicely have been done in a few minutes into something that doesn't solve. It's like that. You're thinking there has to be something here. I don't see anything. That's graphable. So if in doubt, you can graph that, right? And then just see, okay, what am I looking at here? But if you can't factor, just make sure that you check your factorization. So what do we got? Plus 5 minus 3? X squared minus 3 plus 5 plus 2. Okay. You're not going to get the numbers wrong. I mean, surely you cannot have two numbers that multiply to 50 and you cannot get those two numbers wrong. Okay. What you will do is you'll get your signs mixed around. Okay, and then what's this? X minus 3. And here's a hint. Probably one of these guys is the same. Okay. Likely, right? Like, Now, the way you can determine that, obviously, graph it. And if you don't see, here you're looking for, hey, there's two asymptotes. If I don't see two asymptotes, then you know one of these guys should be the same. All right, what are the non-permissible values? 3 and negative 1. Use your work in part B to complete the following statements. At the non-permissible value, x equals negative 1, there is a vertical asymptote. Right? Because negative 1 does not make the numerator 0. So there's a vertical asymptote. And as x approaches negative 1, the absolute value of y approaches, so what's it doing? Infinity. Now, we need to be a little more explicit than that, right? Like, we should be able to describe this so when we graph it, we go, looks just like I thought it would, right? So as x approaches negative 1 from the right-hand side, so here's a number line. So if I'm approaching negative 1 from the right-hand side, this is the right-hand side, then what value am I using? Like negative 0.99 or something like that, right? So we got to think about it. So what happens? If I plug negative 0.99 into this thing, where's it going to go? So here's what we do. Negative 0.99 plus 5, that's a positive value, right? Negative 0.99 minus 3, this is negative. So this will be plus, this is negative, what's this guy? That guy's also positive. So I got plus times minus over plus times minus. So I have a negative over negative, which is positive. So as we approach from the right-hand side, from below, then y approaches, I'm not sure, let me just see the notation that we're writing. Positive infinity. So just go plus infinity, okay? Positive infinity. As we approach from the left-hand side. And sometimes we say from above. The right-hand side is from above. The left-hand side is below, right? We just, above, below. Okay, so let's say we have a number like negative 1.1. What sign is this? It's going to be positive, right? You get negative 1.1, you're adding 5. You're subtracting from a negative, that's negative, that's negative. What happens when you have negative 1.1 plus 1? You get negative or positive? You get negative. I have 3 negatives and 1 positive. What's that going to give me? Negative, right? So up top you have a negative, on the bottom you have a positive, negative divided by positive. So you're going to approach negative infinity. At the non-permissible value x equals 3, there is a let's see, do they say point of? They say point of. They say point of discontinuity. Often we'll just say point discontinuity. But I guess that's more a general. Point discontinuity says that that's here, it's when x equals 3, then that's where there is a point of discontinuity. And that value will be what? Well, what do we got? What does this simplify to? Right, let's just go here. We're going to have y equals x plus 5 over x plus 1. Okay? And then I'm going to put in what value for x? So 3 plus 5 over 3 plus 1 is 2. So there will be a point of discontinuity which occurs at the point 3, 2. So x is 3, y is 2. The x-intercept is, what's the x-intercept? So when does that happen? When y is 0. What's going to make y, you're looking at this, what values make y 0? So y is 0 when, so forget this, right? Y is 0 when this is 0. Okay? But forget the 3, you can't use 3. So it's only this, just negative 5, right? So the y-intercept will be y-intercept, did I say y-intercept? No, that's what I have. The x-intercept is negative 5. Did you make y 0? And the y-intercept is, take these guys. Y-intercept occurs when x is 0. You're going to end up with negative 15 over negative 3, yeah, which is 5. Sketch the graph, labeling all its features, and verify. So now we should be able to draw a pretty accurate graph of this based on all the characteristics that we've developed, right? So sketch in your vertical asymptote, your horizontal asymptote. So sketch in your asymptotes first. Put down your point of discontinuity. Draw a little open circle there. Get your intercepts. All right, so what's all the information that we have? Horizontal. So we have, at x equals negative 1, there's a vertical asymptote. Okay, so let's do this. I'm just going to label that down here. X equals negative 1. Did we do horizontal asymptote? Yeah, we did. Y equals 1. Y equals 1. Okay, what else? We have a point of discontinuity at 3, 2. So let's throw in a little scale here. I guess that becomes 1. 1. And okay, so I've got some points on there. So here's 3, 2. Okay, and what else? We have intercepts. Intercept was the x-intercept is negative 5. Now there, so there's the x-intercept. And the y-intercept is positive 5. That's up here. Okay, so what's happening? Well, we said as you approach negative 1 from below, or from the right-hand side, you go to positive infinity. So I'm coming at it from the right, going up, and this is coming down. Well, don't go through there. This is coming down and approaching y equals 1. From the left, this is coming from above. It's going to come up here. So it comes from below. So we said as you approach x equals -1 from the left-hand side or from below, you're at negative infinity, and then you're rising up. Domain, what's the domain? So what can't x be? Can't be -1, it can't be 3. And what can't y be? Can't be 1, and it can't be 2. Okay, so graph that on your calculator, and I'll graph that on here, just so we'll have something else to look at. But you want to look at it on your calculator. So what have I got on the bottom? X squared minus 2x minus 3. And what have I got up top? Plus 2x minus 15. Okay, so here's our vertical asymptote. There's our intercept, 0, 5. Here's our intercept, -5, 0. Here I am tracing along, and when we get to 3, we have undefined. Close to 3, we have the value 2, right? That's how we know it's 3, 2. Like looking at this, we would know, oh, well, it should have been 3, 2, but you can't do that. Okay, what's left? A little summary box. If a rational function has non-permissible values, then at each non-permissible value there will be a what or a what? So vertical asymptote. And remember, it's a vertical asymptote, it's not a horizontal one, right? Horizontals are as what happens when it goes to infinity. Vertical asymptote is when the denominator becomes 0 and the numerator does not become 0, or a point of discontinuity. It's going to make 31 a lot easier now that I know what you're going to know coming out of 30. The blank form of the equation will indicate which it will be. So the factored form, right? We have to factor it. You have to factor it. You have to factor the denominator, if nothing else, just to find out where there is what may be a vertical asymptote or point discontinuity. Factoring the numerator then tells you what they are. A value of x that makes both the numerator and denominator 0 corresponds to a. So if both numerator and denominator are 0, what have you got? Point of discontinuity. A value of x that makes only the denominator equal to 0 gives you what? Vertical asymptote. A value of x that makes only the numerator equal to 0. So if the numerator is 0, we have 0 over something, which is equal to. So if the numerator is 0, right, and the denominator is not, I will have 0 divided by a number which is equal to 0. I end up with y equals 0, right, which is what? It's the x-intercept. So you get the x-intercept. The x-intercept occurs when y equals 0, right? When do you get an x-intercept? When y is 0. When is y 0? Well, if the numerator is 0 but the denominator isn't, then I have y equals 0. What's that? It's the x-intercept. It occurs when y is 0. So those values of x that make y equal to 0 give you the intercept. If it makes both 0, it's a point discontinuity, and if it makes only the denominator 0, it's a vertical asymptote. Okay? So zeros all around. Numerator only being 0, it's x-intercept. Numerator and denominator, point discontinuity, only the denominator, vertical asymptote. For the function 4x squared minus 1 over blah, state the equation of the horizontal asymptote. Okay, what's the horizontal asymptote? Y equals what or what? 2 over 3. 4 over 6 or 2 over 3, right? Y equals 4 over 6. You can start with and then just write y equals 2/3. So you should try and simplify where you can. If you go directly to 2/3, that's fine. Determine the, so determine means you have to do what? Show the work. So you'll never see the word determine on the multiple choice section of the exam. You'll never see the word determine on the diploma because you cannot show work. Now you might see it in the sense of, you know, John determined the point of discontinuity to be this by following a series of steps. Where did he make his mistake? Okay, so then it shows you a set of steps being, you're like, oh, this got factored wrong, and so you've got the wrong thing. You thought it was this, and it was that. Determine the equations, the vertical asymptotes. So what do we have to do this? We have to factor everything, right? So we need to get this in factored form. So the top is luckily a nice difference of squares. Here's my bet. I'm going to bet there's a 2x plus 1 or a 2x minus 1 as the factor. Okay. Now, because one of these is going to cancel, right? Likely. I mean, come on, you got to get a point of discontinuity. So which would it be? So then I'm going to need a 7 and a 1. So they're going to give me. So this will give me a 14. And this will give me a 7, and I need it to be a plus minus, so I get 6x squared minus 14 plus 3. Wrong. Plus, didn't do that on purpose, by the way. It just kind of happened that way. Even the best of us make mistakes. And I'm not the best of us. So 6x squared plus 14 minus 3 is plus 11 minus 7. Okay. Yeah. You do this, though. So that's how easy it is to make a mistake. That's how easy it is to fix the mistake. I almost wish I did it on purpose as a teacher, but you know, it happened, but that's how easy it happens, right? You get your signs wrong, and then you check, and you go, I'm going to end up with a negative 11, I want a positive 11. Okay, what happens if you do that? These still cancel, but you're now thinking there's a point of discontinuity here when there isn't. It's here, right? So you're thinking it's a negative 1/2, it's a positive 1/2. If you go to graph this, it's not going to look right. It's like, what? Okay. Okay, so in fact, determine the equation of, so we're going to write, so what are the vertical asymptotes? What's the VA? X is equal to negative 7/3? Come to the realization. It's okay, take a moment. Oh, right, yeah, got that. Okay, what is the point of discontinuity? One half, but it says the point of discontinuity, right? Which means we need the rest of it. So the point of discontinuity occurs when x is a half. So what does that lead to? So 2 times a half plus 1 over 3 times a half plus 7. Okay, so what I'm going to do is I'm going to put a half into, I'm going to get rid of these two guys and put a half into here and here. Ending up with 2 times a half is 1 plus 1 is 2. And 3 times a half is 3 halves. Oh, God, fractions. What fractions? 3 halves plus 7 is 7 is 14 halves. It's 17 halves. I'm going to multiply by 2/17. Okay, wait. So this is over 17 halves. So it's 2 times 2 over 17. So it's at 1/2 and 4 over 17. Use your calculator and then just convert it to a fraction. I hate fractions divided by fractions. It's fractious. Okay? So that's how that one works. Is there more? No, that's it, right? It's just, so all we're doing here is just we're stating some characteristics as we're not asked to graph it. I mean, you can be pretty certain that on the quiz you're probably going to be asked to graph something or some things. But if you're not, you know, one of the biggest things on the quiz is to do what? Read the question. Are they asking me for the x-coordinates of the invariant points, or are they asking me for the coordinates of the invariant points? Right? So make those distinctions. Everybody on the weekend is going to go through the quiz, right? The practice quiz. I wish I could monitor how many times it's been downloaded. I don't know. Maybe I can.
For example, if you had a function y equals 4x cubed over x squared,
Yep.
you have to take out an x, or how do you do that? And the
Well, so 4x cubed over x squared would simplify to 4x. So it would be the same as the graph of 4x, except it would not be defined when x was 0. So there would be a point discontinuity. Write the equation of the write the equation of the okay, here we go. So this kind of puts it all together. What have we got? We have a vertical asymptote here, right, at x equals 2. Okay, so let's sketch that in. And let's make a note, right? VA at x equals 2. We have a point of discontinuity. And where is it? -1, 3. We have a horizontal asymptote where? Okay, so we have an HA at y equals 2. Okay, we have an x-intercept of, so x int of, it's called 7/2. It has 3.5, but if I want to turn that into a factor, then it'll be 2x minus 7, so 7/2. And we have a y-intercept of
3/2.
Now, okay, this we really don't know for sure. Okay, like I don't see a dot there. I'm guessing. So what I'm going to do is just hold it in reserve for now, and just sort of say, okay, if we work everything else out, do I need to know that, or will that just have come out anyways? Okay, but this we know this is the point 3.5. Okay, so we're going to start with, and we're going to say, all right, this equation is going to be of this form. Y is equal to A. And then we have what? So we have a point discontinuity at x plus 1. So there's an x plus 1, or sorry, x minus 1. So there's an x plus 1 here. There's also one up top, right? Because those have to cancel. So also at x plus 1. Okay, we have an asymptote where x equals 2. That translates to what down here? X minus 2, right? Okay, so if x equals 2 is the 0, that's where there's a 0. Then x minus 2 is the factor. All right, what other information do we have? We have the x-intercept. Now, the x-intercept occurs when y is 0, so forgetting about this, what's going to make this 0? Well, that's the x is 7/2, right? So if x is equal to 7/2, then 2x is equal to 7, and the factor is 2x minus 7. Okay, so let's just kind of label these while we're here. So this is the point of discontinuity. This comes from the vertical asymptote. This comes from the x-intercept, and also point of discontinuity, that comes from there. So the point of discontinuity gave us the x plus 1 top and bottom. The x minus 2 gave us the vertical asymptote, and the 2x minus 7 gave us the x-intercept. So we know, let's see if we can extend the page. We know that in the simplified form, okay, in the simplified form, let's throw brackets around the x minus 2. The simplified form gives us the coordinates of the point of discontinuity, right? So I'm going to use the simplified form along with the coordinates of the point of discontinuity to calculate the value A. Okay, so simplified form says, so use simplified form, use simplified form, and coordinates of the point of discontinuity. Okay, well, we're just working this one backwards, right? All the other ones we work from, okay, I got a factor form, and then I factor, and then we get all the information. Here, we're given all the information, we're kind of working bottom up. Okay, so we know that, what? Y equals 3 when x equals 1. Okay, so we just solve for a. What do we get? It's negative 1? You're right, it's negative 1. Negative 1. Okay, so that's negative 3. So it's going to be negative 9 is equal to a times, what do we got? Negative 9. So a is 1.
Mr. Adams,
Yeah.
how can you use the point of discontinuity where it's a point not on the graph to find something?
Okay, so how do we get the, so if you look back at the previous examples, how do we get the point of discontinuity? We substitute the value of x into the simplified form. So if we have the simplified form, which is sitting here, with some a value because we don't know what a is, and we substitute in the point of discontinuity, right? So normally we'd have a value of a, we'd throw negative 1 in here, we'd get out the 3. This time we have the 3 and the negative 1, we can work out the a. So, you know, previous examples, there's already an a value, we already know that. We substitute into this with the x coordinate from here of the point of discount, we get the y coordinate. Here, we know the point, so we just throw that point in, we solve for a. So in this case, a equals 1, and ultimately, what did it ask for? What's the equation? So the equation is y is equal to, and it said in simplified form, so x plus 1 over, okay, and then we just multiply that out, right? Simplified form. That's factored form. Well, we go back to the original. This is the equation. Because a is 1 now, right? Okay. And then we can, okay, what do we get? 2x squared minus 7, so minus 5x minus 7. And x squared minus x minus 2. So there's our factored form with the value of a, right? So remember, anytime you're finding equations in any of this stuff, there's an a. You don't know what it is, right? You get that from a point. We're not going to assume. See, we could have assumed this was the point. Maybe it is. But what if it isn't? Okay, so here's the question. Is it? What if I put in 0 for x? What do I get? 1, 1, 0 here gives me negative 7, and 0 here gives me negative 2. Yeah, it actually is 3.5. So that would work, right? But this is a point, and this, it was going right through the line, so that's also a point. What do we got? One more? Write the factored form of the equation of a rational function with the vertical asymptote at x equals a half. So I'm just going to change this into 2x minus 1. Right? So if I see x equals a half, that's the root. The factor is 2x minus 1. An x-intercept of negative 3/4. Okay, so what's that going to be? 4x minus 3? 4x plus 3, right? Sorry. So, yeah, 4x equals negative 3, 4x plus 3. And a point of discontinuity at 318. Okay, so we got y equals a. Got a point of discontinuity at 3, so there's a factor of x minus 3. Since it's a point of discontinuity, it's also up top, right? It's also in the numerator. We have an asymptote at x equals a half, so there's a factor of 2x minus 1, and we have an x-intercept of negative 3/4, which gives us a factor here of 4x plus 3. Okay, we cross these guys off. We put in the point 318, so we go 18 is equal to a, 4 times 3 plus 3, over 2 times 3 minus 1. So a 18 is equal to, what do we got, 1215a over 5. So 18 is equal to 3a, and a is 6. Okay, or you could go 120 equals 15a, but that's more difficult. Okay, so our equation in, what did they ask for, factored form?
Yeah.
Yeah, okay, so y equals 6. I'm going to throw the bigger numbers up front, so 4x plus 3x minus 3, and on the bottom, 2x minus 1, x minus 1. Okay, thus endeth the unit. Okay, so we're done, and we're done the unit. So you've got the weekend, you've got Monday. Monday is, we're going to start trig, whose timeline covers the front and back of the page, because trig is very extensive. Test is on Tuesday, which makes it what period? Last period of the day. Okay, so any extra timers who cannot stay after school, see me before Tuesday. Okay, so if you could stay after school, cool. We'll leave you in a room to write, and if you can't, then we'll have to make arrangements.